So today we are going to start the next chapter, chapter number 9, work, energy and power. First, let's talk about work. So if we talk about what is work, the basic definition of work is when a body is displaced, please pay attention on this, when a body is displaced by the application of force in the direction of displacement. Please pay attention on my words. When a body is displaced by the application of a force, an external force acting in the direction of displacement, then a work is said to be done by that force for this displacement. Please pay attention on this. Whenever a body is displaced, you can say when a body is displaced by the application of an external force by the external force F in the direction of displacement then a work is said to be done by that force F for the displacement S. For that displacement, you can say S. This is the basic definition. So you need to understand that work is done by that force and for this displacement. This is the major point of the definition. So work is a mechanical form of energy transformation, we can say, because if I go in a very depth, work and energy, they are just two faces of the same coin. Means you can transform work into energy as well as energy into work. It is very important to understand. You can transform work into energy as well as energy into work. So work is mechanical form of energy. When there is a displacement, there is a movement due to the consumption of energy, then you will say a work is done. So work is mechanical form. Work is mechanical form of energy. You need to pay attention on this particular line. Means whenever there is a mechanical movement in a body due to the application of force, then you will say that your energy consumed is transforming into work, or you can say simply a work is done. So if we try to formalize work, so let's say you are applying a force, an angular force. That's not necessarily that you are applying a force always horizontally. So you are applying a force F vector, but your force one component is actually displacing the body in this direction. We know it very well, resolution of vector. So the body has been displaced from O to P by the displacement S vector. Now this force is making an angle with displacement, that is theta. So theta is the angle between the displacement vector and the force vector. Theta is the angle between F vector and S vector. Keep this thing in your mind. Do not say theta is the angle between force and the horizontal line. Don't say it. Always read it like this, that theta is the angle between force vector and displacement vector. So definitely a work will be done, but this time if we go through the definition, only that force is responsible for the work due to which there is the displacement. Only that force, not the entire force. This force is having two effects. One along the displacement and another is perpendicular to the displacement. that is Fx and Fy. So only Fx is responsible for this displacement. Definitely, if you are applying a force vertically on a body and you are saying that it is moving horizontally, it is not possible. Only vertical movement is possible if you are applying a vertical force. So only Fx is responsible for S. So work done will be studied for Fx. So work done by force Fx, it would be W equals to. So now please you need to pay attention. The original formula of work is actually greater force you are applying, greater energy it will be consumed or greater work will be done. So work is directly proportional to force in the direction of displacement, means Fx. Work is directly proportional to displacement also. Greater displacement is there, means greater energy is consumed to move that body with that great displacement. So greater work is done. So you need to pay attention. After combining these two formulations, you will get W equals to, here constant is 1. So W equals to Fx into S. And what is Fx here? So Fx is the horizontal component of F force, and if this is theta, it would be F cos theta. We have proved it in resolution of vector. So Fx is F cos theta. So the universal formula for work done is W equals to F cos theta into S, or you can write like this, W equals to F S cos theta. So this is the original formula and the universal formula for work done, means force into displacement and the cos of angle between them, angle between force and displacement. This is the original formula for work done. And if we talk about vector form, work is a scalar quantity. W is a scalar physical quantity because it is another phase of energy. We have discussed it. So it is a scalar quantity. But the problem is force is a vector quantity, displacement is a vector quantity. So definitely work is the dot product of force and displacement, because force into displacement is giving you a scalar. Two vectors will give a scalar outcome when they are in dot product, means F vector dot S vector. You can write like this. So this is another way to represent dot product. And SI unit, so same as energy. So SI unit of work is joule. SI unit of work is joule. While if we talk about CGS unit of work, it is same as energy, that is erg. And 1 erg is 10 to power minus 7 joule. We have discussed it already in unit conversion system, dimensional analysis application. So this is the original formula for work done. F vector dot S vector means dot product, or you can write Fs cos theta. It will be totally dependent on the given quantity in the numeric problem. If they are giving you in the vector form I cap, J cap, K cap, then you can go for dot product like this. And if they are giving you magnitude and the angle between them, you can go for this formula. But keep this thing in mind, in this entire process we are assuming the force is constant, means during the whole displacement there is no change in the force. This formula is not applicable for we can say variable force. For variable data we should go for calculus method. So if we talk about calculus form of the same formula, it would look like this. If F is a variable force, for a variable force, let's say the body has been displaced by a very small displacement A to B. This small displacement is ds vector, for which a small work will be done. For a small displacement, ds vector, a small work is said to be done. A small work dw is said to be done. So if I talk about instantaneous for that small work done, you know it very well, the differential form, it will give you the value of momentary data or instantaneous data. So the formula will get modified, dw equals to f ds cos theta, where f is instantaneous force. You can write f instantaneous. Let me highlight this for you. You can write F instantaneous means momentary. F instantaneous. And if we talk about maximum work done means when theta is actually 0 degree, you will get cos theta is +1. So this is maximum positive work done. You can go for the cases. It is a childish thing for you now, because in 9th class, in 10th class, you have studied about the possible 3 cases of work done: positive work, negative work, and 0 work done. When theta is 90 means when the force and the displacement just acting perpendicular to each other. In that particular case, theta would be 90 and cos 90 is 0. So that is 0 work done by that force for this displacement. In the same sense, maximum positive work done, maximum negative work done, theta 0, theta 180 respectively. So this is very simple. Right now I am talking about simply calculus form for the maximum positive work done. So dW equals to F instantaneous ds only. In vector form even you can write it, but right now I'm only taking scalar quantities. So you can write or you can modify the calculus form like F instantaneous equals to dW by ds. It is giving you the instantaneous force or the momentary force for a particular displacement, means the differentiation of work with respect to displacement or change in position. So this will give you the instantaneous force data. And if you want to find out the work done for the entire given range, means what will the work done from we can say the displacement from x1 to x2. If the position initial position is x1, final position is x2, and small displacement is dx, let's say it is dx vector. So what will the work done? Let's modify this formula. Even you can write it like dx, not ds every time. If you are studying displacement in terms of x-axis, you can write it dx. You are familiar with this calculus form. Now we need to use this form, that dW equals to, for maximum, dW equals to F instantaneous ds, integrating both sides. I am talking about this. If you want to find out the total work done in the given range, integrating both sides, same calculus method. For the given range we should go for integration. For momentary data we should go for differentiation. So integrating both sides, what will you get? Integration of 1 dW work done, let's say 0 to W, initially work done is 0 and finally it is W, equals to F instantaneous, and F is a variable force, so definitely it would be dependent on X. So F instantaneous dx or ds as you wish according to the data, and limit of displacement or position is x1 to x2. So this is the basic blueprint for, we can say, work done for a given range. Now even you can modify this whole entire thing like integration of 1 is W simply, because it is being done in with respect to W. So it will become W. Let's say equation first. This is the equation first. W equals to. Now you can't assume force as a constant because we are talking about a variable force which is dependent on position. So this is the blueprint, x1 to x2, differentiation of x with respect to x. So this is a blueprint for calculating work done in the given range of position. So this is called the calculus form. It depends totally on the question. If they are talking about to calculate the work done in the given range, you will go for this. If they are talking about to calculate the force at a particular moment, at a particular position, you will go for differentiation form, this one. So there are two calculus form of this work done concept. Now let's talk about the graphical manipulation for this work done. If we try, let's take two cases. One, when force is constant, first case is when force is constant, and second case is we are talking about variable force. So if we try to plot a graph between force and displacement for an experiment, and right now I'm talking about still positive work done, not negative. So positive dimensions we are taking. Force versus displacement graph. Force versus displacement graph. X-axis, Y-axis. It is a graph. Please pay attention on this. Same here. Force versus displacement graph. Even this thing we had studied during the introduction of calculus method in the earlier classes. So whenever the force is constant, means for the entire displacement the force is not going to change. It means it will become parallel to x-axis. This graph you will get, and if I try to find out the area under the graph, this area lying under the graph definitely will give you the value of F into S, and F into S is actually work done. So the area under Fs graph will give you the value of work done. The area under Fs graph, it will give you the value of work done. You need to pay attention on this. So this is the major conclusion which will be effective for both cases. So area under Fs graph, force position graph or force displacement graph, or you can say Fx graph. Don't say, not every time it is called Fs, it is also called Fx graph. Area under Fs graph or Fx graph gives value of work done, even with sign, value of work done with sign even, because this value, if this graph is lying in negative quadrant, so definitely it will give you the negative work done answer. And if we are talking about a variable force, means force is getting changed with respect to position. Suppose first the force is increasing, then it is decreasing, so it is completely a variable force, but still area under the graph will give you the value of work done, means still this area will give you the value of work done. So this time the work done will be calculated by calculus method, means you will choose that smallest portion for which force appears to be instantaneous as well as constant. You will choose that particular smallest fraction, and that smallest fraction with respect to displacement is called ds or dx. You know it very well. And the area of that small fraction will be small work done, because area will give you the value of work done. So this small area will give you the value of small work done, and for this force would be F instantaneous. F instantaneous it would be. So this is completely simple interpretation for variable as well as constant force. Still the area lying under the graph will give you the value of work done. You need to pay attention. A numeric problem can be asked by giving the graph that calculate the work done for that particular graph. So you will be able to calculate it with the help of this area under the graph. And if you are having the variable force, so definitely you will go for the differentiation integration method, which we have discussed already.